Piero Naldesi. He's a postdoc at the Institute for Quantum Optics and Quantum Information in Innsbruck. His research interests focus on out of equilibrium quantum many-body systems. And today he's going to talk about persistent current dynamics and fermionic rings.
Thank you for the introduction and for the, say, capability to put like, to build up this conference. I mean, I've been in the first, like, I've been the first time in the Atomtronics conference 2 years ago, and I really appreciated the, say, the familiar feeling that you can, that you have, and I mean, I'm really looking forward for the next edition that hopefully will be in presence in 2022, and I'm also really happy to see that the community is really growing, and that there has been a lot of new results, really interesting. So let me just present myself a bit better. So yes, I'm working now in Austria, in Innsbruck, in the ICOCI lab. But in the last years, pre-pandemic, I was working in Grenoble in the group with of Anna Minguzzi and Luigi Amico. And we have been working a lot on bosonic and fermionic systems and giving my small contribution to the field of Atomtronics. And here are some of the works, if you want to take a look. If you have any questions, I would really be pleased to discuss about it. And this brings me to the outline of my talks. So today I will discuss fermions in 1D rings. And the talk is divided in 2 parts. The first one, I will discuss the physics and how to detect the main qualities, the main aspects of the VCSBC crossover. And in the second one, I will discuss the phase coherence and how to detect the different type of phase coherence of a Fermi gas. Okay. Let me spend some words for my collaborators. And I want to say that like all the work that I've been presenting now, it has been done, I mean, almost all the work during the, during quarantine. And I mean, I think it's really something that we ended up with really nice results, really nice physics during this period that has been really stressful for, at least, I mean, for me for sure, but I think for everybody. So I'm really pleased to have such great collaborators. Okay, so you probably already know Luigi and Anna. So the other PhD student is Giovanni, that is working in Grenoble, and he will have a poster in the later, I think today, poster session. And if you want to take a closer look at all the results, you can look at these 2 papers that are now in a preprint in archive. Okay, so let me do just let me spend a few words on introduction on Atomtronics. I think you will be already by now full of details on rings and different structure, but I just want to say that with the technology that we have now, with the controls that we have now on quantum gases, we can create tightly confined rings, and that can be continuous, or they can be lattice ring by superimposing spatial modulations. And we can create, as we saw also today, we can create bosonic rings and fermionic rings. And the atomic cloud can be put in motion with different techniques. For example, they can be steered with some lasers, and the rotation can be detected. So by performing absorption imaging, we can see if the atomic cloud is has a current or not. And what I want to add to this is that what we saw, what I want to try to convince you today is that by measuring the noise-noise correlation from this absorption imaging, but at different time of the expansion, you can study the VCSBC crossover. You can observe parity effect and the doubling of the periodicity of persistent current in the back regime. And you can probe different type of phase coherence of the Fermi gas. Especially, you can probe the phase coherence of the wave function, and you can measure current, and for a few for a small number of particles, you can count the particles that you have in your state, and that you can observe many coherence at the level of many many particles, observing pairing and quasi of diagonal long range order. Okay, so let me tell you a bit more the type of setup that I have in mind that we can use to observe all the results that I will show you in the following in my talk. And the idea is that at t equal to 0, we prepare a state, an initial state that is composed by a lattice ring and a blob in the center. And when we release the trapping, this blob in the center will be a reference frame for the rotate if the condensate around is rotating, and will help us detecting eventually currents. And we want to perform two types of imaging, one at intermediate time, and another one is that in the far field approximation at a really large time, where by measuring or we have a correspondence between the density correlation at different position and the density correlation in momentum space of the initial cloud at equal to 0. Okay, so let me just move to the first part of my talk, VCSBC crossover. So the VCSBC crossover, we have already had a really nice description, but I will briefly describe this phenomenon. It is a phenomenon that appears in gas of fermions, of spin 1/2 fermions, with attractive interaction. So by increasing the value of the interaction, we go from a VCS regime where we have weakly bound pairs, and the coherence size of these pairs is much larger than the interparticle distance, to another regime where we have tightly bound pairs that they act as point-like bosons. There are different phenomena that appears in the two regimes. One is the parity effect. So in the VCS, I will discuss much better everything. This is just a resume of the results. So in the VCS, we can observe the parity effect. So the system behaves differently if the number of pairs is even or odd, while there's no parity effect in the VC. And the fact that the pairs are tighter and tighter bounded going from the VCS to the VC regime reflects in a halving of a period of the persistent current. Okay, let me discuss the first thing is the parity effect. So the parity effect can be explained easily if you consider a gas of a spin 1/2 fermions composed by 2n particles, and we have n up, spin down, n up fermions with spin up, and the same amount of particles with spin down. And the system behaves in different ways if the number of pairs is even or odd. So if the number of pairs n is even, the system is paramagnetic, meaning that if we apply a small flux to the system, the energy decreases. while if the number of pairs is odd, the system behaves in a diamagnetic way. So by applying a small flux, the energy actually increases. So you can also see this feature by studying the current. That is just is proportional to the derivative of the ground state energy to the flux that you apply. And really important, this phenomena is not present for fermionic system. Sorry, is not present for bosonic system. Is a characteristic of fermionic system. So the second part is the second thing that we need to consider is how the system reacts in the presence of a rotation or of an external flux. So to answer to this question, we can use the Leggett theorem that says that the periodicity of the persistent current is fully given by the flux quantum that we have in our system. So it depends only on this and does not depend on details of the interaction of the Hamiltonian or local disorder. In particular, this in our system translates in the fact that the presence of tighter and tighter pairs, it reflects in a halving of the flux quantum in our system. So the periodicity of the persistent current is reduced by 2. Let's now go to some results. So we model the crossover from the BCS to the BEC regime with the two Hamiltonians. One in the BCS side, we use this method was proposed years ago and it's well established. So on the BCS side, we describe the system with the Fermi-Hubbard Hamiltonian, and we analyze a system of 2n fermions, half with spin up, half with spin down. J and U are J is the hopping amplitude, and U is the attractive interaction between the fermions. While in the BC side, we describe the system with the Bose-Hubbard Hamiltonian, but we consider n bosons without spins and with different hopping in the interaction, that in this case will be repulsive, to reflect the fact that you have pairs in your system. So these two systems, these two Hamiltonian can be analyzed. So the Fermi-Hubbard can be solved by Bethe-ansatz, while the Bose-Hubbard is not integrable, and the only way to get results are numerical simulation, and in this case we perform DMRG analysis of it. And we calculated the ground state energy from which as a function of the flux, for which we obtain the current, and the expansion of the density correlation that I was describing before. And I show now the results for the energy for the currents in the two regimes for an even and odd number of particles. So on the left, we have a system made of 4 particles, 2 spin up, 2 spin down. On the right, 6 particles, 3 with spin up, 3 with spin down. We used a small number of particles just to let's say, to enlighten the features, but I mean, for a larger number of particles, you will have got different numbers, but exactly the same physics. Okay, let me now show you that the presence and of the parity effect and in this case. So at weak interaction, what we see is that for an even number of particles, okay, I cannot see the screen. Okay, I see now. So what we can see is that the parity effect disappears while we increase the interaction. As you can see, like for an even number of particles, increasing the interaction, there's a state that at flux equal to 0 comes down and makes the system pass from a paramagnetic phase where the energy decrease, increasing the flux, to a diamagnetic one, where the energy actually increases while applying a flux. While for an odd number of spin-up particles, the system is always diamagnetic. From these results, we can also obtain the fact that the periodicity of the persistent current is doubling. As you can see, passing from weakly bounded pairs to strongly bounded pairs, the periodicity actually is actually doubling. And this reflects the fact that you have a formation of strong pairs in your system. And let me now show you that, let me now convince you that you can get the same information from interferograms that you obtain measuring correlation in different position at intermediate expansion time. So these interferogram are obtained for a small value of flux, 0.1 omega 0. And as you can see, for n even, the current remains always 0. We stay always in the first parabola of the energy. And the increasing the interaction, our interferogram doesn't change qualitatively. And while if you analyze the entry spin-up, so 3 spin-up results, what you see is that by increasing the interaction, the interferogram changes because actually you are changing the circulation of the state. So at small interaction, you are in a state with current, while for a larger interaction, you pass to another one where you have no circulation. So this is perfectly reflected on the structure of the interferograms. And so if you perform the same analysis at different fluxes, you can see that you have a doubling of the periodicity of the persistent current. So you compare two different values, 0.1 and 0.4. And what you see is that since the two states are in the same parabola, so they have the same current, they are in the state with the same angular momentum, the two interferograms are the same. So at weak attraction, you see that both for n equal to 4, equal to 2 and n equal to 3, the two interferograms are the same. While if you go to stronger interaction, to the VEC limit, so the two interferograms at 0.1 and 0.4, they are different, reflecting the fact that one of the two states passed to a higher angular momentum. And this is an effect that as we said before, it doesn't depend on the number of particles, but it's always present. It reflects only the fact that you actually have the presence of tightly bounded pairs in your system. And let me now move to the second part of my talk on the presence of on how to prove the phase coherence of a Fermi gas. And I will try to show you that with the same methods proposed before, and so by analyzing interferograms obtained at different time, you can access different type of coherence of the system. Okay. So the first type of coherence that we have in mind is the one at the level of the wave function. Okay, so in general, the many-body wave function is complex valued. So we can associate a phase to this function. And for a bosonic condensate, such phase coincides with the single particle phase, since all the particles contribute coherently to the many-body state. Okay. For fermions, that's not the case, and there's no simple analytical relation between the many-body phase and the single particle, since all the particles contribute incoherently with a random phase. And the second idea of phase coherence that we want to study is the one related to the fermionic pairing and superfluidity. So to make this concept emerge in our experimental protocol, we compared the repulsive and attractive interaction. And we will observe that very different features emerging in the two regimes. And these features are strictly connected to the pairing and to the quasi of diagonal long-range order, making the different coherence of the state for repulsive and attractive interaction appear.
So you have 9 minutes left.
Perfect. Thank you. So to assess these two types of coherence, we use to, as I said before, we analyze two different quantities, but that can be extracted for the same experimental setup. So we analyze the density-density correlation during the expansion at the intermediate time and at in the long time limit, where we have access to the density-density correlation in momentum space. And okay, analyzing the interferograms obtained at intermediate time, at intermediate expansion time from the density-density correlation in real space, we see that for bosons, a clear phase structure emerges as a characteristic spiral. And we know that counting the number of branches, we can obtain the circulation, the angular momentum of the state. While for fermions, I mean, even if we say that all orbitals contributing coherently, a spiral emerges from an interference that is not completely destructive, and it also allows us to measure the current in this in our system. In addition to this, what we have is that the Pauli principle induces a specific dislocation pattern that allows us to count the number of particles, at least if we have a small a system with a small number of particles. And we obtain actually this relation for which the number of dislocation that you can see, like here, are quite clear in this interferogram, are one less than the number the number of spin up, or well, of components that you have in your gas. And these okay. So we now study the long time limit. We can now study the long time limit of the expansion in the system. And, so in this limit, one, as I said before, one from the density-density correlation can obtain, so sorry, at in different position of space can obtain the density correlation in momentum space at t equal to 0. And so what we have done is we have studied this correlation nk prime for attractive and repulsive interaction. And what we saw is that as soon as we turn on an attractive interaction in the system, a clear structure in the antidiagonal kk, like kk prime, emerges indicating the presence of correlation between K and K prime, so the presence of a BCS pairing. And on top of that, we have studied the visibility of this diagonal K equal minus K prime. And by the scaling of the visibility respect to the number of particles, we saw that our results are compatible with the presence of quasi-off-diagonal long-range order in the system. So
5 minutes remaining.
Good. So we can clearly say that by analyzing at infinite time noise-to-noise correlation in momentum space, you can test, like you can obtain you can obtain if there's a BCS pairing in the system. Okay, with this I conclude. Actually, I'm a bit I went too fast, I guess, but maybe there's more time for if you have some questions. And I want just to say that if you're interested, you can also join Giovanni to the poster session that we have later today. I think, thank you for the attention, and if you have any question, I would be pleased to answer.
Thank you. So, questions? Anybody? Let's see, somebody has there.
Where should, so I see one in the question and answer.
Okay, answer the one in the question and answer.
Okay, so Matteo asks me on something on slide 2. One could nicely see that there is one defect much more pronounced than the others, where the red pattern actually bifurcates. Yes. What does it correspond to?
So yes, maybe I can tell
yes,
you where do I mean. So let's say more or less in coordinates, I would say.
Yeah, you mean this one?
Yes, this one where actually the red line actually splits into two, right? So if you follow the spiral, the first red spiral splits into two. So I just wanted to understand better. Let's say at 0.1 in terms of coordinate, 0.1 and minus 0. Whatever 3 or so. Something like that.
Yeah. This part.
Yes.
In the
that one. Yes.
Bottom left.
Mm-hmm.
Well, actually, I'm not. I don't know. I cannot give you an answer for which this one is. I cannot give you a quantitative answer for which this one is a bit different from the others.
Okay.
Maybe I can comment. So,
of course, yes.
Yes, Luigi, thanks.
Hi, Matteo, how are you?
Hi, all good.
So, yeah. Say, it's not a splitting to my view. It's not a splitting. So basically, there is a dislocation of all the spirals. You see. So if you follow the first spiral, then this should continue in the internal one.
I see. So in some sense, it's the signal that you have finished your counting and you have completed the dislocation. So in terms of
yes,
every dislocation is 1/7 of a full dislocation, and once you are finished, you are dislocating by a full spacing, and therefore you restart. Okay, now I see. Okay.
Like
yeah, but it's. I mean,
okay.
For bosonic system, it's really easy to make this kind of analysis. For fermionic, it's a bit more difficult because, I mean, each particle contributes in a more messy way.
Mm-hmm. Okay. Okay, thanks.
And also, I can tell you that like the part that you see that is more red is because is in correspondence to because when you calculate nr prime, you have to fix one point.
Yeah. So I was not
Okay.
worried of the contrast. So
Okay. So yes. Okay.
good. Thanks.
There is
There's one more question in the Q&A.
Always a question.
Okay.
Molina, I don't know who he is, but I think yes.
I have a question in question and answer that is thanks. In the last noise correlation slide, can you comment on the structure for the attractive case? What information do they contain about the initial state of the system? For the attractive case, okay, it's more interaction. You already see that like the structure is completely different from the attractive, from the repulsive one, and that you start to have like this part on the diagonal that gets, let's say, more and more relevant respect to the background. And like by increasing, if you keep on increasing the interaction, you have these big correlations on the diagonal k minus k prime that indicates the presence of tightly confined pairs. You asked me what information do they contain about the initial state? Let me also say again, that like so there's a relation for which like at infinite time, if you analyze the interferogram in particular position, maybe I wrote it here. Yes, and in particular position R, so in particular position R, you get the like the correlation nk prime of the state at t equal to 0. So you have this kind of let's say correspondence between correlation in position space at t infinite with correlation in momentum space at t equal to 0. I hope I answered, otherwise you can ask me again.
I think Omalina's hand is now lowered. So
can you hear me?
yes.
Yes. I would like to ask you about the last, the transition where you make this description with these density plots. Yes, well, well, I have to say that I am not a bit surprised of your result, because if you look at, for instance, when you have a mixture of bosonic species, when you have a transition from if you plot the ground state of the momentum distribution in two dimension of momentum space, so you get basically the same result. So from positive, you have a diagonal fringes, and if you go to the negative, you have these anti-diagonal fringes. So I mean, what is the difference between? I know that this is case you have, you are dealing with fermions, right? So, but in a sense, is similar, because in that case you have a mixture of two type of bosons. So, but then you have a similar, behavior. So you have a per superfluidity behavior, which is basically similar to what you call here VCS, right? So,
yes, okay. I have to admit that, like, I'm not super familiar with mixture of both Fermi. Yes, both Fermi, but this is something that we have also. Let's say it was something that he wanted definitely to explore, and maybe I mean it would be really interesting to discuss.
Yes. Okay.
So, can I comment?
Yes.
Yes. So I think I agree. It's not surprising. So in the time of flight, so in the infinity, so in the time of flight picture, you see differences, right? But here the context is different. Basically, what you do is just a single experiment in which you make interference, a condensate in the middle with the ring. It's the single one, right? So, and the message here is that at intermediate times, you see the particle phase coherence. right? And in the same experiment, if you wait longer, then you are able to trace whether the system is quantum coherent in the sense of off-diagonal long-range order or not.
Okay, you mean this is dynamical process?
This dynamics in the T infinity.
Yeah. Okay.
So somehow
Yes.
here disentangle between two things. That is a particle phase coherence. In disentangle is not wrong. Is the wrong word. So you analyze the interplay between the two concepts. Okay. So here with this experiment, you are able to see and to study operatively. So you make an experiment to study the interplay between these two concepts: the particle phase coherence and the quantum phase coherence in the sense of quantum phase of matter.
It's really possible that you can apply the same, let's say, methods to the system that you have in mind, but I mean, so it's a way.
Yes. Yeah, so to complete, also if in the system you studied there are k minus k correlations of your pairs, you will see in the diagonal. So it's it's a really very general method.
Okay.
Good. All right. So I think with that, we will move on to the next talk.